Hello, and welcome to Astronomy 100. In today's segment, we're going to talk about the concept of keeping the passage of time understandable for us to be able to use it as a tool. When early humans became aware of the concept of time, there was the need to describe the concept of past, present, and future. Today, it's something we take for granted, but in the early days of humanity, there was a need to be able to mark the passage of past, present, and future. And so what the astronomy of this is that the people of the early days were able to use the idea of things occurring regularly in our universe to be able to show the passage of time occurring past, present, and future. And so when we look at the sky, there are a couple of conveniences that come built into the sky that allow us to understand this concept. For instance, the sun is something that we see every single day. And of course, the sun appears to rise in the east and set in the west every day. And so this regular, methodical movement of the sun across the sky can be used to mark the passage of time. Another example is the moon. The moon is something that shows a different appearance over a period of time. We call this the phases of the moon. And as the moon shows its changing appearance over time, it will do a process of showing a variety of ways that it looks, but then it starts all over again. So in this picture here on the screen on the right, you can see that the moon changes its appearance, and as time goes by, it goes all the way to the end, and then it starts all over again. So we can use this time that it takes to go through all the different phases as an increment of time. So the origins of timekeeping are related to astronomy. And even though we live in a very modern world, it is still very much related to astronomy. So let me prove this to you. The first idea we're going to talk about is the concept of solar time. And the words solar time refer to time measured with respect to what the sun is doing. And in today's world, we're very technological when it comes to time. You may have some very sophisticated digital device that tells you what time it is. But what I'm going to show you is that even in today's world, our timekeeping devices are still actually referring to what the sun is doing. So let me show you the progression of this. In the early days of humanity, we used what were called sundials. The purpose of a sundial is that when the sun is out in the sky, the post that sticks out of the center of the dial will cast a shadow based on the sun's light, and as the sun crosses the sky, the shadow will move across the face. And the regular movement of the sun across the sky is indicated by the regular movement of the shadow. And as long as you have this dial incremented in a certain way and calibrated, the movement of the shadow can be a way of telling the passage of time related to what the sun is doing. Now, of course, there's some problems. For instance, a sundial does not work at night. A sundial does not work when the weather is cloudy. And so there are features to it that are useful, but of course features to it that make it inconvenient. So as time went by, the progression was to make a sundial in concept become mechanical. This is a grandfather clock where the box has been removed and the inner workings of the clock is now visible. You'll notice the springs and the sprockets, but you'll notice the face of the clock, the face of the grandfather clock, is still a dial, very much like the sundial is. Notice how it's incremented in a particular way, just like the sundial is. And the hands on the clock, as they move around the dial, are very much like the movement of the shadow across a sundial. So this mechanical clock is just a mechanized version of a sundial. Well, the problem with a grandfather clock is they're very large, they're not portable, and if you want the ability to take it with you to know what time it is, it's not very convenient. So what we did was shrink it down. And so this wristwatch, if you were to open up the back of it, would have springs and sprockets. It has a dial on the face. It has hands, just like the grandfather clock does. There's a regular movement of those hands. So this is essentially a portable version of the grandfather clock. Now you might say this is very antiquated. Most people don't tend to have watches like this anymore if they have a watch at all. You might say, I use my cell phone to figure out what time it is. Well, the thing is that the numbers that are represented on the cell phone are simply a digital version of what this wristwatch is showing you in a mechanical way. And this wristwatch is a shrunk down portable version of what the grandfather clock is showing you. And the grandfather clock is a mechanical version of what the sundial is trying to show you. So even though we may live in a modern world, the digital clocks that we use are still showing you the concept of solar time. So solar time is time measured with respect to what the sun is doing. Now, this leads us to the first increment of solar time that gives us the very common word day. Technically, it is referred to as the solar day, and by definition, the solar day is the time that it takes the sun to complete two successive crossings of the meridian. To fully understand this, we need to define what the term meridian means. So let's show you what that is. The meridian is an imaginary line that crosses the sky. So in this illustration, here is the person standing out in the middle of the field. Here is their horizon. You can see north, south, east, and west. And we have an imaginary line that stretches from true north all the way through the point directly overhead, all the way down through the point of true south. So this line that connects true north through the point directly overhead to true south is what we call the meridian. Think of it as a line that divides the sky in half. There's a western half of the sky, and then there's of course the eastern half of the sky. In addition, the term zenith describes the point directly over the person's head. So the point directly over your head or anybody's head is called your zenith. So by true definition, the meridian goes from true north through your zenith through true south. So this line is the line that's being referred to in this definition. What this means is if you watch the sun rise in the east and then work its way across the sky, it's going to cross the meridian. And if at this point you started a timing device, such as a stopwatch, and timed how long it took the sun to set in the west and then work its way all the way back around, come up in the east and cross the meridian a second time, or two successive crossings of the meridian, you will have measured how long it takes for the sun to go all the way around the sky, one full cycle, one full 360-degree movement of the sun across the sky. And if you use your timing device, what you will calculate or what you will measure is 24 hours. So the solar day is 24 hours long, and you might look at this and think, well, that's kind of a nice convenience that the solar day ends up being exactly 24 hours. In reality, the 24-hour period of time is the definition of the solar day. So the idea is, many thousands of years ago, when people noticed that the sun makes one complete journey across the sky, it was decided to call that 24 hours. So in other words, it was forced to be a 24-hour period of time. We could have made it anything we wanted to. It could have been called 10 hours, it could have been called 30 hours, it could have been called 17 hours. But it was chosen to be 24 hours. And the reason why is because back in those days, mathematics was base 12 rather than base 10. So it was decided to make it two increments of 12 to equal the solar day. So 24 hours is the forced definition or the forced number that goes with the concept of the solar day. Now remember, the sun is not really moving across the sky. The appearance of the sunrise all the way across the sky to the sunset is really the rotation of the Earth on its axis. So the solar day is demonstrating that the Earth is turning, and the sun is simply the object that we're looking at that proves to us that this is actually happening. Now what I'm going to do is illustrate this for you. And this illustration, we'll let it run a couple of times. Notice the idea is the sun is directly overhead, and then as the Earth turns on its axis, we go back to having the sun directly overhead. This is looking down on the North Pole, and so the natural rotation of the Earth combined with the Earth moving in its orbit. So the turning of the Earth and the Earth revolving around the sun, moving in its orbit. But you'll notice something kind of interesting here. For the sun to be directly overhead, and then come back to being directly overhead again, if you look very carefully, you'll notice that the Earth actually has to turn more than one full rotation. So in reality, the solar day is not the true time that it takes the Earth to spin one time on its axis. The solar day is actually more than one complete rotation of the Earth on its axis. So the reason why this occurs is because we are using the sun to measure this period of time, but it is the sun that we are orbiting around. So we have to turn more than 360 degrees to come all the way back to lining up with the sun again. So if we were to say, how long does it take the Earth to turn once on its axis? The answer is not 24 hours, because 24 hours is a little bit more than one full rotation. So how do we fix this? Well, astronomers use a term called sidereal day. And you'll notice the definition looks fairly similar to solar day. It is the time it takes for two successive crossings of a celestial object other than the sun, the moon, or the planets across the meridian. Now let me show you what I mean by this in an animation here. We're going to start off lining up with the sun, but what we'll notice when this comes all the way back to start again, if we ignore the sun, but instead we line up with a very distant star, way off in the background. Notice that when the Earth turns on its axis, we line up with that very distant star once again, and then the Earth has to turn a little bit more to line up with the sun. Now you might say, well, wait a minute, these are two different places. But remember, the stars are very, very far away. So pointing straight up, and then in the next position, pointing straight up again, is essentially pointing at that very distant star. You'll notice that the Earth will complete one full rotation when you line up with the distant star once, and then line up with that distant star a second time. The Earth actually completes one full rotation. And then it takes a few extra minutes to line up with the sun again. So the sidereal day is the actual time that it takes the Earth to turn one complete turn on its axis. And if you measure this, you'll end up with 23 hours, 56 minutes, and 4 seconds, a little more than 4 seconds. And there is, of course, a difference of 4 minutes between the solar day and the sidereal day. And so in reality, because we're locked into this concept of solar time, and when in reality it's not a true representation of the Earth rotating on its axis, the true rotation ends up being 23 hours and 56 minutes. And so in reality, what that translates into is that when you look at objects in the sky that are moving across the sky, rising or setting, they will rise 4 minutes earlier each day. So if you look at a particular star rising tonight at 8 o'clock, tomorrow night it rises at 7:56. The next night it rises at 7:52, and so forth. So celestial bodies will appear to rise 4 minutes earlier each day, and it adds up over time. And all of this simply has to do with the fact that the Earth is turning on its axis while it is also simultaneously revolving around the sun. Now, the putting all this together creates one important concept related to the constellations, and that is that the constellations are seasonal. What we see in the sky tonight will not be the same constellations that we see in the sky in a few months from now or 6 months from now. Let me show you what I mean. If we're outside at midnight and the constellation of Orion is directly overhead, 2 months from tonight, or a month from tonight I should say, you'll notice that directly overhead it will not be Orion, it'll be some other constellation directly overhead because the Earth has moved a little bit in its orbit. And then 2 months from the first time we looked outside, 2 months later, you have a completely different constellation directly overhead at midnight. 6 months from the original observation, you now have the Earth way over here, and it is a completely different set of constellations that are out in the sky at night. So what this means is that the constellations that you see at night are steadily changing night after night after night because of the Earth revolving around the sun, and as we rotate on our axis showing different constellations at night, slowly changing night after night. Now, the important part to understand about this is the slow, steady changing of the constellations is what allowed the humans on Earth to understand the concept of the year. 1 year's worth of time would be the time that it takes for the constellations to steadily change night after night after night and then start all over again. An example is, if there's a certain constellation directly overhead tonight, that constellation won't be directly overhead at exactly the same time until a full year from now. So if you go outside tonight at midnight and you see Orion directly overhead, tomorrow night at midnight, it won't be exactly directly overhead. The next night, a little bit different. But a full year from now, Orion will be back to directly overhead. And so this is how the early people, the early humans, were able to understand the concept of the passage of time using the celestial bodies. Now we're just about out of time, but in the next segment, we'll continue with the next idea. I hope you'll join me.